Okay, so how many probabilities for this network? Okay, let's see. How many here? Oh, okay. How many here? One. How many here? Two. Because what are those? Probability that sprinkler given cloudy and probability of sprinkler given not cloudy. Why don't you need probability of not sprinkler given not cloudy? It's just 1 minus that. Right? Okay. And then this one is just probability of cloudy given nothing. Given nothing basically is the prior probability. Because this guy is an orphan. Cloudy is orphan, has no parents. Okay? So it's just you give probability of cloudy. How about this again? The same thing. 2. How about here? 4. They will be of this kind. Probability of wet grass, given sprinkler and rain. Probability of wet grass, given sprinkler and not rain. Probability of wet grass, given not sprinkler and rain. Probability of wet grass, given not sprinkler and not rain. Okay? You all get that? If you don't, then you're going to have lots of fun in today's class. Okay? Because we're assuming that you understood this. Okay, so how many would you have actually needed to specify this network? I mean, if you have, how many entries are there in the joint probability distribution? How many entries are there in the joint probability distribution? 16, because it's 2 power 4. Actually, yeah, 2 power 4, 16. So how many of them do you have to specify? What can you, how many degrees of freedom do you have? 15, because 2 power 4 minus 1 are the numbers you can specify, so that they can all add up to, yes?
If it was cloudy and then wet grass was on the same level as sprinkler drains instead of 2.
Which what? No. The number of, okay, so here's the thing. The number of joint probability entries depend only on the number of variables. That's it. That does not change at all on the network side, on the way the network is given. Right? If I tell you there are 4 Boolean variables, you know there will be 2 power 4 entries in the joint probability distribution. That's basically the number of rows in the truth table. It's just that unlike the truth tables, here you give some numbers for each of the interpretations. This is how likely you are likely to find that word outside. You see what I'm saying? Okay, and I asked this thing in the end of last class, and let's see what is the least number of numbers that I can provide. I mean, what would be the topology of the network such that it would require least number of numbers? No edges whatsoever. So basically, it would look like this: cloudy, sprinkler, rain, wet grass. You see what I'm saying? Now, some people last time thought lines, chains are somehow easy stuff. Let's look at a chain too. And in fact, one of the interesting things about Bayes networks is everything that you ever heard of is a special case of Bayes networks. So it's like a huge unifying theory. Okay, almost. Except by itself, Bayes networks can't do it. There's one other thing we won't talk about in this class called Markov networks or Markov random fields. Together, they essentially unify everything that you know about probability. Okay, in terms of probabilities, probabilistic distributions. Okay, but imagine the following thing. So suppose I have this cloudy, and then sprinkler, rain, wet grass. That would be a chain, right? You guys all agree that's a chain. Okay. So how many does that require? First of all, does that have a name? If you have a network like that doesn't have a special name? When did you think of chains to begin with? And first of all, in general, I ask these kinds of questions during the next few classes. It will be either Bayes something or Markov something. Markov chain. You guys know about Markov chains? That's a Markov chain. Do you see what I'm saying? That's a Markov chain. And how many does this require to specify? That's the fun part. You can just, by looking at it, you can give how many numbers are needed to specify. Okay, how many are these required? Okay, that's right. This is 1, 2, 2, 2. So, equal to 7. Okay? 7 is clearly less than what you needed here, which is 10. Right? 4 plus 2, 6 plus 2, 8, 9. Okay? Seven is less than 9, but 7 is way more than 4. Right? How do I get the 16? How do I get the 16? So this one is kind of a middling network, right? This one is the happiest network in the sense it requires the least number of numbers to be specified. And to some extent what it is saying, we realize that essentially the topology of the network tells you independence assertions that hold in the probability distribution. And the independence in probability distributions factorize the probability distribution. Okay, these two things I will make sure that you understand by the end of the class. At least in my mind, I'll try to make sure that you understand. Whether you understand it is a completely different issue. So factors, so basically think of probability distribution as a big matrix. If you make, basically what you're trying to see is, can I get this big matrix as a sort of a multiplication of smaller matrices? Not exactly matrices, it turns out, they are actually join operators. We'll talk about the semantics. Okay, and you already kind of know this. The reason you love independence assertions is the following. If I ever ask you what is the probability of A, B, C, D, and A and B and C and D are all independent, then what do you say? It will be probability of A times probability of B times probability of C times probability of D. That's how probabilistic reasoning ever gets simplified. Okay, a big joint entry will become a multiplication of smaller entries. Do you see what I'm saying? You never add, you multiply. So in fact, it's factoring that will wind up being important. When you talk about independences, independence factorizes the probability distribution in different ways. Each probability distribution, in terms of its topology, the moment I give the topology, which is basically the graph structure, it corresponds to a particular form of factorization. Okay, so the last thing I was going to ask with respect to this is, can we draw the network that will actually require, so you realize that no Bayes network can ever require more than 15 numbers, right? Because 15 is the absolute worst. That's the total joint distribution. If you're asking for more than 15, then you're making up stuff from somewhere. So there should be a Bayes network that will be the worst possible thing, that will require all 15. Just as this is the best possible in terms of the least number of numbers needed, they should be the worst possible. Let's try to write that. Okay, let's just start with cloudy. I'll just make a cloudy. Then I put sprinkler. I'll put a link. Then I'll put a rain. I'll put a link from everything to this. Okay? Then I put a wet grass. And then I put a link again from everything to this. Do you see that network? Is this cyclic? There are no cycles. Let's see how many numbers does it need. This one will take 1. This one will take 2. This one will take 4. This one will take 8. 8 plus 4, 12. Plus 2, 14. Plus 1, 15. You get this? This, by the way, is called, so you guys know the notion of a complete graph? A complete graph is basically every pair of vertices are connected by an edge. That's a complete graph. You know this. Please say you know this. You went through the entire computer science program. Okay? So a complete graph is one where each pair of vertices are connected by an edge. A cyclic graph, on the other hand, should have half of those edges missing. Right? Because otherwise it will start putting cycles. This is a complete acyclic graph. It's a complete acyclic graph on 4 vertices. Any complete acyclic graph on 4 vertices, if those variables are Boolean, it will basically require the full joint distribution. In essence, by doing this, what you are saying is that the probability distribution essentially cannot be factorized. There is no way of simplifying the probability distribution other than giving essentially all joint distribution numbers. In essence, because you're giving it in a different way here, the joint distribution numbers will all be of the form probability, cloudy, and sprinkler, and rain, and wet grass, and with polarity is changed. But here you're only looking for the numbers which are all conditional probabilities, because you ask here, for example, probability of rain given, sprinkler, and cloudy. But you still require 15 numbers. You still require 15 numbers. So you don't get anything additional. So this probability distribution is unfactorizable. So if you want to have analogies in your mind, this probability distribution is a prime number faculty. Prime numbers don't have factors. And this is a highly composite number. And somewhere in between are the rest of the networks. Every possible directed acyclic graph that you can draw on cloudy, rain, sprinkler, and wet grass will correspond to a Bayes network. And that makes its own certain independence assumptions. Okay? Now, since we're talking about this, here is this other question that I have, and we'll kind of come back to this later, but I want to ask you this anyway right now, just so that you start thinking about it. Imagine you are from Mars, and you have no idea what cloudy means, sprinkler means, rain means, wet grass means. Because you actually have an idea here. So when I'm putting these links, you kind of say, you can't write this. You probably say you can't write this. Right? Because you'll say, how can you say that cloudy is independent of sprinklers? Typically sprinklers don't come on when it's cloudy. How can you say cloudy is independent of rain? Rain is highest chance of falling if it's cloudy. How can you say wet grass is not connected to anything else? It's of course connected to rain and sprinkler. Do you understand what I just said? You are bringing in the semantics you have for these English words. If you're from Mars, hopefully you won't know what these names mean. And you would be from Mars if you are working, let's say you are trying to help some biologist in Biodesign Institute. And they find that, we found this alpha, beta, gamma, and delta proteins. Okay, alpha, beta, gamma, and delta proteins. I just said proteins because I have no clue what those are. Okay, and maybe you know, but for you, for computer science people who are basically helping these biologists trying to model the dependencies, they have no clue whether alpha is dependent on beta beta and gamma is dependent on beta, whatever. Do you see what I'm saying? One of the things you would like to hope to do is you will see data involving alpha, beta, gamma, delta, or data involving cloudy, sprinkler, vectors, day. And from the data, learn the Bayes network. Right? That's what you like to do. Okay? So then when you try to learn the Bayes network, you have to understand in the back of your mind that there are two things that you have to learn. One, you need to learn the topology. Second, you need to learn the numbers. Notice till now I didn't put any numbers on this network. We could have this much interesting discussion without putting any numbers. You see what I'm saying? Okay? So when you're trying to actually figure out what is the network, you need to first get the topology and then get the numbers. Which one do you think is the harder part? Getting the topology or getting the numbers? Getting the topology is a much harder part. In fact, as we will see, given the topology, getting the numbers is actually quite easy. Getting the topology requires understanding the connections between variables. And it's a much harder thing. So, since getting topology is hard, typically what you will try to do is, if you are not learning topology yourself, you will try to go ask an expert, give me a topology. So Martian will come to you and say, this is your planet, tell me how these things are related. And you might give this as a network, or this as a network, or that as a network. Okay, and once you give the network, the Martian then learns the numbers from the data. Okay, now here's my question. Suppose you too are a bit sort of iffy on the connections between cloudy, sprinkler, arrays, and vectors. It's one of these things where the Martian thought you're an expert, so you thought maybe I'm an expert. You have no clue either. So you are being asked to put these links. Kind of are not sure whether anytime you put a link from one node to another node, you are saying there is a probabilistic dependency between them. Right? So now you have a choice. If in doubt, should you put more links or less links? Do you understand what I just said? If in doubt, should you put more links or less links? What happens if you put more links? So what exactly are you optimizing by putting more links? You are ensuring that the learned distribution is actually connected to the real distribution. If you put less links, then the best set of numbers you can get with respect to this network will still never be able to approximate the real distribution to the extent you think there are more dependencies. But here is the other question. Don't you have this tension in your mind that if you say more, then one idea would be that anytime somebody comes and you say, oh, everything is connected to everything. And you can't be wrong. What is wrong with doing that?
You won't be that right either.
What?
You won't be that right either.
No, you will be right.
You
will be right. You will be right. You could be wrong for a slightly second order reason that I'm not sure you would get yet. But think of computation. Think of the cost of learning. Imagine, anytime I'm talking about Bayes networks, think of neural networks that you know and love. And realize that they are just 4 cousins of Bayes networks. Except they actually work. Okay? So, imagine I'm trying to learn some particular concept using a small Bayes network or a big Bayes network. If somebody tells you, you will do pretty much the same whether you do the small or the big Bayes network. Which one? Small neural network or a big neural network? A shallow network or a really deep network? I tell you, you will do almost the same irrespective of which network you use. Which would you rather use? Small. Why? It's easier to learn. There are much fewer parameters to learn. What are the parameters to learn here? the probabilities. The more dense the network, the more complete the network, there are more probabilities. Remember, one of the things, anything that can be learned with a shallow network can also be learned with a big network in neural networks. What's the problem? In addition to the computational problem, which is that there are more parameters to learn, there is another problem we talked about. Data is less, but another problem.
The size of the solution space?
Something deep about machine learning. Yes, overfitting. You can learn a big network, but you will overfit the heck out of it. So it's sort of like saying, I'll give you data like this. Oh. Yeah, okay, data like this, right? You could, if I tell you fit a line, you will fit a line to it. If I tell you fit something up to 100th order polynomial, 100th order polynomial. Remember, 100th order polynomials will be a huge superset of lines, because lines are just first order polynomials. What would you do in that case? You will basically, to reduce the training data, you pick something like this. That's overfitting. Anytime you think of overfitting, think of that picture. Okay? So yes, you can always cover your bases by saying, yeah, just assume that everything is connected to everything and leave me alone. And they can never sue you. If you are the expert who have to take legal liability, they can't sue you because you said everything is possibly dependent on everything. But then they are likely to do pretty bad learning, both because of computational reasons, these Martians we are talking about, and because of overfitting. If you understand this, you understand a whole lot about how Bayes networks and neural networks and machine learning works. Okay? And one last thing is, you guys said, if in doubt, go with the complete network. If in doubt, go with the complete network. I want to ask this following question. Imagine the ground truth is this network. This is actually the network. But you decided to learn this network. Can you guarantee me that the joint distribution you get using this would be corresponding, would be equivalent to the joint distribution here? Yes or no? How many of you think yes? Raise your hands. How many think no? Raise your hands. So, remember what you did and realize that if you raise your hands for no, you are wrong. It's important to remember that. Okay? So, because the idea is you can never go wrong in terms of, if everything else, like machine learning works as it's supposed to work, then the joint distribution you get here would be the same as the joint distribution you get here. You know why? You know why? Because if this is the real distribution, then I will know probability of CL, probability of SP, probability of rain, and probability of WG. Right? I will know these numbers. If I know these numbers, I can convert into a joint distribution. I can fill in all the 16 rows. If I fill in all those 16 rows, then every number this guy asks, I can reconstruct it from those 16 rows. Do you understand what I just said? So it looks much more complex, but it's exactly the same in terms of joint distribution. That's the reason why you were right when you said, I can't go wrong by assuming more links. By assuming more links, you cannot go wrong. If on the other hand, if this is the true distribution, and this is what you are trying to learn, that guarantee doesn't hold. if you assume there are more dependencies than truly are there in the world, you cannot go wrong. It's like, if you are paranoid, you can never be proven wrong. Paranoia basically means everything is connected to everything. Okay? If on the other hand, if you are optimistic and think everything is independent of everything, you can be proven wrong. Without how can, me having fun during Thanksgiving break be connected to my grade? You could be proven wrong. I'm not saying you will, but you could. Right? So that's something that you want to understand. Look at this slide. If you can understand this slide at the end of the class in a true sense, you basically understand Bayes networks and the issues in learning. Everything else is details. Any questions before I go forward?
For the probabilities to be the same, the graph on the right has to be complete and acyclic, so all dependencies to all.
No. Again, all I'm saying is, if this was ground truth, if this were, let's say, the true ground truth with the numbers, etc., okay, then any topological network which has more edges than this, which has a superset of edges that are there in this, will always be right. Because you are assuming more things are dependent, you might find that some dependencies actually don't have to work. If on the other hand, so this is the same idea. If I allow you, this is the same idea as what's going on here. If I allow you to look up to 100th order polynomial, that means I'm also allowing you to look lines. So in theory, if the best fit is a line, you should be able to find it. The reason you don't find it is because you do wrong kind of learning. What's called non-Bayesian learning. This is why we'll talk about Bayesian learning, and then you say that's the right way to do it, but nobody does it because it's too costly. Instead, you do what's called maximum likelihood estimate based learning, which is what everybody else does, which is basically just directly look at each hypothesis, pick one hypothesis, winning hypothesis. And that can actually be wrong in the sense that it might totally overfit to the data. It's the same idea. If I allow the hypothesis space to be a bigger space, then clearly you can't go wrong. If I make it smaller space, if I gave you a data that is generated by a parabola, and I tell you look for a line in it, and you decide to look only for lines in it, then you're guaranteed to be wrong. You get that? Again, adding extra lines, extra links to a Bayes network is just like increasing the expressiveness of the hypothesis by increasing the order of the polynomial in the decision surfaces. If you understand that, you're ahead of the game, way ahead of the game. Because a whole bunch of people don't understand. Okay? Any other questions? Yes, sir.
Are we still using the assumed probability like we were doing in the last class, or are we finding the probability?
We right now, so the first part of the lecture is right. The first part of the lecture, today's as well as tomorrow's and Wednesday's lectures, we first talk about if somebody gives me the probability and the topology, how do I do the reason? But then you notice today I already foreshadowed. If they don't give it to you, what would be involved in doing learning? We'll come back to learning next Monday. We'll do both. We'll do everything. Yes.
Could there be a Bayes network in things like this?
No. Bayes networks are directed acyclic graphs. Markov networks, on the other hand, have different semantics. They have undirected edges. And it turns out that basically, in the universe of all the, so basically in the universe of all the joint distributions, some of them can be handled by Bayes networks, some of them can be handled by Markov networks, and some can be handled by both. But I'll only talk about Bayes networks here because it's too many. Okay. Yes?
Can you restate what corresponds to having a higher polynomial or higher order?
Higher polynomial means basically I'm saying I gave you this data. I'm sorry. Okay. I gave you that data, those dots.
Yeah.
And then I said, look for the best fit polynomial up to size and up to degree. And if I say up to degree 1, only lines can be formed. Up to degree 2, you can find lines and parabolas. Up to degree 3, you can find lines, parabolas, and cubics. Okay, now as I say up to, as I increase the degree, I am including lines as well as parabolas, as well as cubes, as well as more things. The point is, this is also called, in the neural network parlance, this is called, I have been calling this the expressiveness of the hypothesis space. How many different hypotheses can you consider? Okay, it's also called capacity. In the context of neural networks, they call it capacity of the networks. The bigger network, so imagine I started with some network, right? And then I just made it bigger. That means the new network has more edges than the old network and more layers than the old network. It's a superset. Clearly everything that the old one can learn, the new one can learn. There are certain things new one can learn, the old one can't learn. And so the newer one is considered as have a higher capacity. But then the higher capacity networks might basically can overfit. Because they have this higher capacity, they might actually, to learn the numbers correctly and the weights correctly in the neural network, they need a lot more data. If you give less data, they're likely to overfit. And there are ways of getting away from overfitting. What did we talk of as a possible way of getting away from overfitting in neural networks? Dropout. And what did I say when I said dropout? I said it's just a form of Bayesian learning. So there is this Bayesian learning that I've spent my entire semester building up. It will come on Monday. Not Wednesday. Okay? Yes.
So if we have this network and we assume this network, so mathematically they should converge because probability of AB is equal to probability of A into probability B if we start observing data. So basically this is independent. So mathematically they should be like same, right?
Not sure what to say. So if this is the ground truth and this is what you assume, you will be fine. If on the other hand, this is the ground truth, this is what you assume, you will not converge.
So mathematically,
No, I'm sorry, just saying mathematically doesn't change anything. Okay. We can talk about this outside, but essentially, if this is the ground truth with numbers that I made, and you believe that this is the topology, I can set up a network that you can never learn. I can also say mathematically, but typically try to avoid saying mathematically. Not just about you, but in general, that's the way people try to intimidate others. Without actually knowing what they're talking about. If you know what you're talking about, amazingly great. But in this case, actually, unfortunately, you are wrong. Okay? Yes?
So the analogy with polynomials is the polynomial suffer
Yeah, the same thing here. You go. So there you're thinking about the values of coordinates. Here you think about probability.